So the medium access protocol, okay, where you need to share your resources, okay, and it's limited because frequency band is very limited in the sense that there's a lot of other usage that can be used, okay, like you can see that the frequency band can be used as a Wi-Fi where you have 2.4 and 5 gigahertz channel. It can be also used for satellite communication. Even it can be used for frequency. So with respect to that, the medium access control, which specifically that use wireless communication, they are very limited on the bandwidth, what we call resources. So what we need to do is that we need to optimize whenever that we have these resources, we need to optimize it. Okay, so these are some of the optimization based on basically what are the challenges that we have. Okay, so you can see that these three different types of multiple access protocol. One we call random access protocol. The term random means that you can actually send your data without having to identify either the access or the medium is currently being used or not. Okay, so you can just send it directly. Okay, then we also have what we call control access protocol. With this control access protocol, basically before you send, you wanted to make sure that you are not colliding with other senders. Okay, so there are few methods that we will see later, but basically if there's a possibility that we can kind of listen before we send, that is what we call control access protocol. So with this control access protocol, the sender will first what they call it, listen to the channel. If the channel is empty or on idle, so you can actually submit it, okay, or you can submit your data so that it can be sent. Okay, and then we have another one, channelization protocol. In this being used as a modern cellular technology, basically what they do is that they divided it into frequency domain, time domain, and also code domain. So that is where you have this FDMA, TDMA, and also CDMA. So they will give you some period or some frequency that you can use so that you're able to transmit. Okay, but again, as I mentioned, if you have very few numbers of users, then should be okay. But if you have a bundle of users, so then we will have to be much more do some optimization. Okay, so these are the different things of multiple access protocol. And if I can go back, okay, on this page 3, so we can see that for random access protocol, we will see the kind of Aloha, carrier sense, multiple access, then carrier sense multiple access with collision detection, carrier sense multiple access with collision avoidance. Okay, and then for control access protocol, okay, we can have what we call reservation, okay, pooling, and token passing. Okay, so the token passing is similar to what we have already seen on fiber optics communication, where you have the ring and you have to pass the token to those who wanted to send. Okay, you append the information with respect to the token. Okay, so that is what we will see also later lah. Right, and then also we have these channelization protocols, okay, where we can see that you can use frequency to be subdivided. Okay, that is why they call it frequency division, multiple access. You can subdivide it into time, okay, meaning that you give the whole frequency to one user, then but you limit the time, okay, so that the other user will be able to also access it on the different time. Okay, and you can also what we call code division multiple access, which actually manipulate both frequency and time lah, right? So basically here it says that when nodes or stations are connected and use a common link called a multi-point or broadcast link, we need a multiple access protocol to coordinate access to the link. Okay, so if you have multiple users and you wanted to make sure that all the user we have the access to the resources, okay, in this sense, we are talking about our frequency band. Okay, so you need to have some protocol that coordinate all these things. Okay, so who can send first, or perhaps before they send, they have to listen first, and so forth. Okay, so there are many formal protocols have been devised to handle access to the shared link, and all this protocol belongs to a sublayer in the data link called media access control. So this is under media access control. There's another MAC that we perhaps we have gone through, what we call media is a MAC address, okay, where is part of the data link, okay, that given the access to all other users to be connected, but by having its physical address. So it's a different MAC. This is for the MAC media access control, which actually manage the resources. Okay. So being identified as these three different types, okay, where the random access protocol used in LAN and WAN at one time, okay, and also you can have a control access protocol which used in local area network, okay, and also you can have the channelized protocol used in cellular telephony, okay. Even now you have other medium or protocol like what we call OFDMA, okay, so orthogonal frequency division multiple access, okay. That is the current techniques that being used, whereby rather than just you are playing with your time and also your frequency, but also you can also have another within your segment where you can also play around with another column, okay, which we won't cover it, okay, but I just want to inform you that there's other types of protocols that can be also used for the channelization protocol, okay. Okay, so coming into the random access protocol, okay, so in random access or contention method, no station is superior to another station and none is assigned control over another. Okay, so basically everyone has the ability to send, okay, any information on the shared link. Okay, so if we talk about this shared link, okay, either it's a physical one or it's a wireless one, basically they have limit of resources lah. So even for your cable, you have very few resources that you'll be able to transmit. Okay, so for instance, if you use your cable, okay, so sometimes it says that the bandwidth limit is 100 Mbps or is 1 gigabit per second or 100 gigabit per second. That's the limitation based on the medium that you are using. Okay, same goes for wireless communication. Okay, we'll see later that you can have this shared medium. Okay, but if you don't really control it, okay, then you will have problem when everyone wanted to send on the same time. Everyone will be collapsing or will be having this collision, and eventually nobody can transfer any data. Okay, so you have to repeat and so forth, and so the user will be frustrated, and then eventually they don't do any data transmission. Okay, so that is what we are trying to address here. So then at each instant, a station that has data to send uses a procedure defined by the protocol to make a decision or whether or not to send. Okay, so this already mentioned that with respect to the standards or with respect to the protocol, we wanted to make sure that everyone can send the information without having to retransmit or perhaps without any error or whatsoever. Okay, so that is what we are trying to see. So this decision depends on the state of the medium, either it's idle or busy. Okay, so if it's idle, then you can send. Okay, or else if you detected that it's busy, you can wait for some period of time before you can send the information. Okay, so we'll see that later also. Okay. So why do we call random access? Okay, because you don't have any schedule, okay, of time, okay, to transmit. you don't have what we call any frame structure, or you don't have any specific channel that you can transmit. So whenever that you think that you want to send, you can just send. Okay, so that is why we call it random access. Okay, so transmission is random among the station. Okay, so if you have a few station to be transmit, then you have to contend with all these few station. But if you have a much greater numbers of users to be transmitted or want to share their data, okay, so there's a possibility that everyone will have problem. Okay, so basically that is why we call random access. You can send whenever that you think that you have any data, just send. Okay, you don't consider anybody. Just like when we are hungry, okay, so what we can do is that we focus on ourselves first, okay, and then perhaps we can see others who are also hungry. Okay, so that's the thing that with random access. Okay, and then you also have contention methods. Okay, because no rule specific with station should send next, and station compete with other one another to access the medium. Okay, so the first thing is that if you want to send, okay, you just send, but basically you have to make contention with others, meaning that you need to make sure that yours is being transferred. Okay, in the same time, others can also transfer their data. Okay, without having no problem lah. Okay, so that is where you need this contention. Sorry. All right. So the first basic and simple protocol is what we call Aloha. Basically, with Aloha is just a simplest protocol which being defined in 1970s, as early as 1970s in the University of Hawaii. Okay, so that is why we call Aloha, because in that slang, okay, they are, when they wanted to call you, okay, they will call you with the term Aloha. Okay, so when it was designed, okay, it's for radio LAN, okay, for wireless LAN, okay, but it can be used also for physical shared medium. Okay, use a simple procedure called multiple access, where the medium is shared between the station, and these are the steps. Okay, so when a station sends data, another station may attempt to do so at the same time. Okay, so just imagine that you have two different user that wanted to send on the same time. Okay, so to whom that you give this priority? Okay, and these two users, do they have kind of consideration before they send? Okay, so that is the question. So when a station sends data, there's a possibility that others also need to transmit data or attempt to submit their data, and they have no carrier sense. Okay, so when there's no carrier sense, there's possibility that what we call collision. Okay, so collision will happen when any of the user will send on the same medium access. Okay, or on the same media access. If more than one is being transmitting, okay, so you can have this collision. And on top of that, okay, when it's collided and both are having problem, okay, you need to also acknowledge if you receive this collision, or if you are having this collision. Okay, so you need to acknowledge the sender, so perhaps the sender will retransmit. Okay, if you don't submit it, they will know, but perhaps after the TTL that we mentioned previously, okay, when you send a packet, okay, it will start a counter, okay, and the counter will end. When the counter end and you didn't receive the acknowledgement packet, so it will retransmit. Same goes here. You will wait for the acknowledgement packet, but if possible, you can acknowledge it much faster, then your system will be much more faster in general lah. Okay. So the data from the two stations collide and become grabbable. Okay, means that you have to you have to delete or you have to scrap the information, okay, if it's collided, okay. So what you need to do is that retransmit, okay, of the data collision. So we have seen that you have to retransmit when you have error, right? Okay, you have to retransmit when you have flow control that perhaps overwhelmed. Okay, now we also say that we have to retransmit whenever there's a collision. Okay, so these are the few things that you will see that packet being dropped because of some other environment in the network itself. Okay. So random amount of time, back of time. So basically, before retransmit, there's a term called back of time. Okay, and this back of time, basically, there are few mechanism. It will be based on the actual transmission time, okay, from sender to receiver. Okay, so it will have some additional algorithm for it. Okay, so when you have this collision, so what you can do is that you have to retransmit, but before that, you have to a bit backup lah. Okay, back of time. Sorry. Right. So these are the procedure for Aloha. Okay. As you can see that if you have we have this. All right. And so when you start, okay, basically it starts when you have any information to be sent. Okay. So this is the K is the how numbers of attempts. Okay. So you have 0 attempts starting from 0. Okay. And then without doing anything, okay, where you don't need to identify either somebody else is already using the medium, okay, or without like do any process, okay. So you can directly send your frame, okay. And here, as I mentioned, this is the TTL. Okay, so you wait for the 2TP, where TP is actually the maximum propagation time. Okay, remember that propagation time where you have the TX transmitter, okay, and you have your RX, your receiver. So you are sending from transmitter to receiver. Okay, so this is on the timing diagram. You can draw something like this where going down is increasing of time. Okay, so meaning that you have this TP is the the propagation time. Okay, where you have your data to be sent between sender and receiver. So if you draw this kind of dotted line, okay, so basically the TP is considered as here. Okay, so TP time to transmit. Okay, where if you say that 2TP means that sending and receiving the acknowledgement packet. Okay, so if this is the data and this is the acknowledgement packet, so if you wanted to wait, is that the two propagation time, 2 times the propagation time lah. Okay, so this is why you have to wait. So if you receive it within the period of time, okay, basically the acknowledgement lah. Okay, so you have to decide if you receive it, then you can say that the packet has been successfully transferred, or else you have to resend or repeat it again lah. Or else, okay, you have to try another attempt. Okay, so there's some limitation for the attempt. Okay, maximum attempt means that after perhaps if I can remember, after 14 try, if you still unable to transmit, means that better you quit. Okay. So you have to find another way how to transfer or transmit your information. Okay, so if you try, if you already reach the maximum limit, then you have to abort because you won't have any success. Okay, or else if you are having less than the maximum attempt, so what you can do is that you need to choose R, okay, a random number between 0 to 2k minus 1. Okay, k is the attempt. Okay, so if this is a second attempt, so k is equals to 2. 4 minus 2 is 3. Okay, so 3 is actually less than 14. So you can try to wait a TB, okay, average transmission time, and then you retransmit. Okay, so this is the simple Aloha protocol. Okay, so one example, the station on a wireless Aloha network are a maximum 600 kilometers apart. So this is the distance. Okay, then assume your signal propagate at 3 times 10 to the power of 8 millisecond. Identify the TP, propagation delay time. Okay, so the TP can be calculated as distance over velocity. Okay. So if you can remember, distance is in meters, okay, and then velocity is in meter second minus 1, right? Okay, minus 1. So here basically, if you this is for the unit meters and meters, okay, can be divided, and the second become on the top. Okay, so you will have in seconds. So that is why you have the unit is in second or millisecond or whatsoever lah. Okay, so you have to distance divide by the speed of the light. Okay, and then your k here it says that times 2 times. Okay, so with k of 2, okay, r can be 2 to the power of 2, okay, minus by 1. Okay, but since it started from 0, so you have 4 different options. Okay, 0, 1, 2, 3. Okay, and then it can actually retransmit, okay, at either of these variables, okay, times by 2 millisecond. Okay, so it can be that you can transmit at 0 second, 2 second, 4 second, or 6 millisecond. Okay, based on the outcome of the random variable R. Okay, sorry. Okay, then since Aloha cannot solve problems of detecting if there's any packet or any other user has sent information on the shared link, okay, so we have what we call carrier sense multiple access. So the idea of this carrier sense is that before you start to transmit, you have to listen to the channel itself, okay, or the medium itself. If the channel is idle, so you can perhaps transmit, or you wait for a while before you transmit. If otherwise, if you identify that the channel is currently being used, so you have to back off a bit and then try to transmit on other specific time that being given by the algorithm. Okay. And for the CSMA, carrier sense multiple access, it can be divided into, one is what we call collision detection and collision avoidance. Okay, so for CSMA CD, basically is designed for wired line. Okay, where CSMA CA is a wireless LAN, which we'll see later lah. Okay, so the benefit of this is to minimize the chances of the collision. Collision can still happen, okay, as we can see later on, because although you sense, okay, the channel is idle, but basically when you start sending, okay, that is idle, but throughout the propagation time, others also can be sending on the same channel, then collision will happen during the period of transfer. Okay. So you will see that further improvement can be done, but basically after Aloha, this is another the next level, how you identify to transfer on the shared medium. Okay, so it's minimized. It doesn't actually solve the collision problem. Okay, so the change of the collision can be reduced if a station sends the medium before trying to use it. Okay, so the idea is that you have to sense. So the idea here is to sense before trying. Okay, before you send. Okay, so before you have to sense first. With carrier sense, each station, okay, they need to listen. Okay, they need to listen to the medium before sending. CSMA can reduce the possibility of collision but cannot eliminate this. Okay, so as I mentioned just now, it can reduce but it cannot totally eliminate this. Okay, and you have to use some other modern techniques of multiple access, such as the CDMA and OFDMA. Okay, why it still exists or collision can still exist? Okay, so the answer is here. When the station send a frame, it takes time for the first bit to reach every station and every station to sense it. Okay, basically, if you have multiple frames that you want to send, the first one is the indication to those other user you are trying to share your information or whatsoever. So if the first frame can reach the other station before the other stations start to send, so you can reduce the collision lah. But basically, while you are sending, the user will also try to sense, then they don't receive the information about the collision, so they will also send it. So basically, if you want to send from A to Z, okay, and this is the timing diagram as I mentioned. Going down, you are having additional of time. Okay, so T1 basically is greater than T2, meaning that T1 sends earlier than T2. So during A started to send, you already listen to the channel, okay, and it's idle, and what it did is that it sends an A frame lah, okay. So when during transmission, since Z also trying to have sending data, Z's frame, but you don't receive yet the frame from A, so you can say that right now the medium is on idle. So what Zex did is that it also sent the information at time 2. Okay, and then during both transmission, okay, at time T3 here, collision happened. Okay, so when this happened, acknowledgement of the collision signal will be sent to both party. Okay, and both will stop sending. Okay, and try to back off and retransmit on other time. Okay, so you receive the signal. But if says that if this happen and during this period of time of your waiting period, your what we call the TTL, okay, time to live, TTL, okay, time to live. So if it doesn't receive it, so it will resend. Okay, another the same the first A frame packet. Okay, so that is an example for your carrier sense when there's a collision. Okay, this example to show you that you have multiple frame. This example here, just a single frame, showing you that with this single frame, if it's detected, information will be sent to the receiver and the send both lah, A and Z here. Okay, and it being identified as a collision happened, so you will need to resend. But here, what you can see is that this blue area, okay, actually this whole part, okay, and this whole part, okay, is overlapping between the blue and the yellow, okay. What happened here is that your B, okay, is starting to submit to the channel, okay. So it can go to the left hand side to A, it can go to the right hand side to D, okay. But in the same time, it haven't reached C and D. So the channel, when C sends the channel is currently idle, C also sends not just a single frame, but multiple frames. So you can see that for C, you have this whole frame lah, that you wanted to submit, okay? And the gray represent the collision, okay? So areas where B is signal exists and area where both signal exist. So now we have a lot of collision, okay? As compared to just a single one, you have multiple packets that having problem right now. Okay, so with respect to that, okay, so you can see that the two signals collided and both frames are destroyed. Okay, so you need to recover from this situation, okay, by perhaps resending it. Sorry, I have a very terrible with my throat right now. Okay, so here is again a vulnerable time in CSMA. So basically, when the system be designed, you have to know what's the distance between the sender and the maximum distance between sender and the receiver. So here you can have between A and B, you can have the distance between A and C, but the maximum will be between A and D. Okay, so that it defines a vulnerable time in CSMA by the time that you need to propagate to the maximum distance. Okay, so here the variable time where you send the first packet, okay, and receive the first packet by the user D is called the vulnerable time. Okay, it's the propagation time, but the maximum distance that you need to reach your furthest receiver lah. Okay, so so basically here you can see that for B, okay, it can send much more faster compared to C, and C can also sense the packet that being sent, okay, on the channel much faster than D. Okay, but basically rather than you define the propagation time for B and C, the best thing is that you define the vulnerabilities as the propagation time from A to D, which is the furthest one. Okay. So the vulnerable time is the propagation time TP, and this is the time needed for the signal to propagate from one end of the medium to the other. Okay, so if you have end to end, so you have to identify what is the propagation time maximum of it. Okay. So when a station sends a frame and any other station tries to send a frame during this time, a collision will result. But if the first bit of the frame reach the end of the medium, every station will already have heard the beat and will refrain from sending. Okay, so that's what we have already seen. And figure 9 shows the worst case, okay, where the leftmost station sends a frame at time T1 which reach the rightmost station D at time T1 plus TP. Okay, so this that's the description of this diagram. Okay, so jumping on to the enhancement for CSMA, okay, Khairil says multiple access. So what you can see is that you can also have what we call persistent method, okay, which identify what should be done whenever that you have this collision or when you sense the channel is busy. Okay, so persistent here means that what action that you need to do when you sense the signal is busy or the channel is busy over here. Okay, same goes. It has to identify what it has to be done if the channel is idle. Okay, so both these two question need to be asked to the sender. Okay, and with respect to that, this define the persistent method. So it define the procedures for a station that sends a busy or idle medium. Okay, so if you are asked what's the definition for persistent method, it's actually this part lah. The procedure of a station that sends a busy or idle medium. Okay. So it can also be subdivided, okay, to many division, right? So after CSMA, you have CMA, CSMA-CD, CSMA-CA, and so forth. But also, they are having these two different methods. The first one is what we call non-persistent, and the other one is persistent. Even for the persistent, okay, you have variants of it, one persistent and also P persistent. Okay, so now you have this one, non-persistent, and also persistent. Okay, but for the persistent strategies, you have the one persistent and P persistent. We'll look into it later. Okay. Okay, so what is non-persistent? Okay, so for a non-persistent, basically you try to sense the channel. Okay, either it's busy or it's idle. If you detect that it is currently busy, okay, so say that this time around, okay, so you are trying to identify either the channel is busy and it seems to be busy over here, okay, then you wait for some period of time, then you try it again, okay, and basically here you can see that it's still busy. Okay, you try it on the third time and it's idle, so what we can do is that you transmit it directly. Okay, so here it says that in a non-persistent strategy, a station that has a frame to be sensed, sense the line. Okay, it sends the line, senses, and if the line is idle, the station sends immediately. Okay, so without having any thought of to perhaps on the different strategy is that perhaps rather than you transmit directly, what you can do is that you wait for some period of time because there's a possibility that collision still can happen. So now, without any hesitation, so it will send the information immediately lah. Okay. So if the line is not idle, the station will wait for a random period of time and then sense the line again. So this is what it does here and here. Okay. And perhaps here also, okay, by a random time. And the non-persistent approach reduces the chances of collision because it is unlikely that two or more stations wait the same amount of time and retry again simultaneously. Okay, so the term here perhaps random. Okay, is another term you can highlight here because when it trying to sense, okay, it doesn't sense on the same time. Okay, the period here and the period here is not the same. Okay, you can see that perhaps this one is much more longer waiting, okay, compared to this one which is much more smaller. Okay, so the term here, they have a random period of time waiting and then sense. So with respect to that, there's a possibility that others will also have another random time, okay, and possible of collision can be reduced. Okay, so this one again, it can reduce, but we say that it doesn't completely scrap the chances of collision. Okay, so there's still chances of collision. So non-persistent reduce the chances of unlikely two or more stations with the same waiting time and retry again simultaneously. However, the non-persistent strategies reduce the efficiency. Okay, so this is the negative part of your non-persistent of the network. If the medium is idle when there are stations that are frames to send. Okay, so you have to wait a very long time. Okay, just for the randomize of the timing. Okay, and then we have what we call one persistent method. Okay. In a persistent strategy, a station continuously sends the line. Okay, so here continuously sends, and you have some standard period of time that you can send. Okay, And if line is idle, then it sends the frame, or else it will wait. Okay, so there are two types: the persistent and one persistent and P persistent. Where for the one persistent, if the station finds the line idle, the station sends its frame immediately. Okay, with a probability of 1. Okay. Okay, mind you, when we talk about probability, the range of value is actually between 0 and 1. Okay, so with this, you have a high probability. With 0, you have low probability. Okay, so it cannot be more than 1. Okay, it should be 0 and 1. Okay, so the term probability, when you look later on also here, we will actually say that the probability is between 0 and 1 values only. So this method increases the chance of collision because 2 or more stations may send the frame after finding the line idle. Okay. However, Ethernet use this method. Okay. So to improve that, they use this P persistent strategy rather than you have random, rather than you have a one persistent. With this P persistent, okay. So you have this unique P probability. Okay, so the P persistent is used if the channel has time slot with a slot duration equals to or greater than the propagation time. In this method, if the station finds the line idle, the station may or may not send. Okay, so the station may or may not send the information, meaning that if is sends that it is idle, so it will use the probability P. Okay. So it sends with probability of P and refrain from sending with probability of 1 minus P. Okay, so you have to multiply with this probability number. So the P persistent strategy combines the advantages of the two strategies, and it reduces the chances of collision and improve the efficiency. Okay, rather than you have to wait at a random time. Okay, so with this probability, meaning that you have to wait for a very shorter time. Okay, so this is how it looks like. Okay, so you can continue send it. Okay, but when you send it's idle, so what you can do is that you have to multiply it with your probability. Okay, so it doesn't send directly, so wait for some probability times period of time. Okay, and then you try to send it, but it's currently busy on the next period of time. Then you try to send it on with disrespect of probability again, and it's idle. Okay, you haven't sent it. Okay, then you can try to send it again. Okay, or else you have to wait. Okay, so in this method, after the station find the line idle, it follow this step. With probability of P, the station sends its frame. Okay, and with probability of Q minus 1P, the station waits for the beginning of the next time slot and check the line again. Okay, if the line is idle, it goes to step 1. If the line is busy, it acts as thorough as though a collision has occurred and use a back-off procedure. So before it sends the packet, so it will try to sense the medium of channel. Okay, and with this P persistent, you have a very much more effective time to be to wait rather than use a random period of time. Okay, so these are for P persistent. Okay, this is for the non-persistent, and this is for the P persistent. Okay, so this you can or you can see it. Okay, so here for the one persistent, when you sense it's idle, okay, you can say that you transmit. Okay, if it's busy, if it's busy, then you have to try again on other period of time randomly. But if it's okay, it's not busy, then you can transmit. And then here, for non-persistent, you have to wait randomly if the channel is busy. Okay. Whereas for the P persistent, okay, so you have a random number that you generate between 0 and 1, which is the probability. Okay, so so you will try it based on the probability, and basically you will reduce the amount of time, okay, because you are having the values between 0 and 1. Okay. Right. So to further improve this, okay, so we can say that CSMA can actually avoid collision, okay, by having to sense the channel. But since when the channel happen or if the channel have a collision, so you can actually have quickly improvise or quickly identify. So carrier sense multiple SF with collision detection and carrier sense detection multiple SF with collision avoidance will actually improve further, where it can detect the collision and it will inform the sender of this collision. Okay, so the CSMA method doesn't specify the procedure following a collision, so it doesn't have any collision management. So CSMA was never implemented. So the one that being used is actually with the collision detection, so shortly known as CSMA CD. Okay, as a procedure to handle a collision, and in this method, okay, it can send a frame after executing its persistent procedure. Okay, it can be one persistent or P persistent, but P persistent is much more efficient. So the station that monitors the medium see its transmission was successful. If so, the station is finished. Okay, so if this there's no collision, so it will sense and not just before sending, but it will also try to sense the channel when you are sending, either it's collided or not. Okay, so if it's not collided, it will finish it up. Else, you will wait for the station, okay, and needs a back off time. Okay, so the question here is how long should be back off? Okay, again, it's reasonable that the station waits a little the time first time, more if a collision occurs again, much more if it happens a third time and so on. Okay, so if it's on heavy traffic, okay, so it's best if you can actually wait more longer lah. Okay, but if you have first time collision, so you can actually what they call it, transmit or retransmit at very short time. Okay, but if you multiple times happens collision, so what you can do is that you have to prolong your waiting time lah. So CSMA/CD is used for your traditional Ethernet. Okay. So what happened? Okay, rather than you have to wait for this. Okay, so you can see that collision happen over here. Okay, so it will detect directly because they are currently sensing the channel. Okay, so it will actually sense collision without having to wait until the last one over here. Okay, so here it will send this first bit of C where A, you have the collision detection message over here. Okay, so much more quicker for it to retransmit, much more quicker for it to detect the collision and make abortion, okay, and retransmit. Okay, so this is with the carrier sense multiple SF with collision detection. And then we have also what we call carrier sense multiple SF with collision. This one same lah, collision detection. Okay. Okay. So here minimum frame size requirement. So for a CSMA/CD to work, okay, there we need a restriction on the frame size. Okay, so you need to know what's the frame size. Because you cannot send everything and then everything is being dropped. So it's best if you can put it into a much smaller frame size and then transmit. So before sending the last bit of the frame, the sending station must detect a collision, and if any, or an abort, if any, abort the transmission. Okay, so this is so because the station, once the entire frame is sent, does not keep a copy of the frame and does not monitor the line for collision detection. So basically, here it says that if it's already being transferred on the transmission line, the frame from the sender is not being saved on the sender transmission port, okay, but it will be totally sent and you don't have any memory of that. Okay, so therefore the frame transmission time must be at least 2 times the maximum propagation time TP. Okay, so so you have to make sure that the frame transmission time, okay, is 2 times of the TP, which is the propagation time lah. Okay. So to understand the reason, let us think about the worst case scenario. Okay, basically, if you have end-to-end station and you need to send it to the last or the longest distance. Okay, so it's TP. So and you have to retransmit the enrichment. So you have that 2 TP. Okay, so the requirement. Excuse me, sorry. So the requirement here is that the first station must still be transmitting after 2 TP. Okay, so that's the reason. Okay. Example here. So if you have a CSMA CD with a bandwidth of 10 Mbps, okay, and then ignore the time, okay, and the maximum propagation. Okay, so here it defines the TP is the maximum propagation time is 25.6 microsecond. So what is the minimum size of the frame? Okay, so you know that the T frame will be 2 times of the TP, which is actually 2 times of this. Okay, TP is here. Okay. So in the worst case scenario, need to transmit for a period of 51.2 microsecond. And the maximum frame, okay, would be 10 Mbps times 51.2 microsecond, which is 512 bits or 64 bytes, okay, which is actually the one that being used as the frame standard for Ethernet. Okay, so this is how they identify the size of the frame. Okay, and this slide shows you, okay, the process for CSMA CD. Okay, so you can see that how many attempts that you count over here start from 0. Okay, and then you have number of attempt and you have some maximum type number of attempt, right? If within the maximum number, okay, so you have to back off and wait some TB time, okay, before you retry. Okay, and then you have to also sense while transmit before sending and during transmission. Okay, and if transmission done, okay, and then without any collision, you consider it as a success. Okay, but if it's done, okay, and you you identified there's a collision, okay, you have to send a jamming signal. Okay, send a jamming signal is where you have to identify all the user. There's collision happen, everyone please stop. Okay, so that's what mentioned here, the jamming signal. Okay, or else if your collision is detected over here, transmit and receive. Okay, so you have to do the retransmission again. So here the difference between Aloha and CSMA CD. Okay, the first one is the persistent process lah. Okay, because Aloha is a random one. Okay, but with a CSMA CD, you can have addition this persistent and you can actually reduce the amount of waiting lah. So that's the idea of CSMA CD. Okay. Then the second difference is the frame transmission. Okay. For Aloha, okay, so you kind of transmit the entire frame. Okay. So if you have 10 Mbps to be transmitted, then you will totally submit all it at one go. Okay. Whereas in CSMACD, transmission and collision detection are continuous process. So we do not send the entire frame. Okay. So not sending the entire frame and then look for a collision. Okay. Because if you send everything, you won't have the information at the sender side being retrained or being stored. Okay, so rather than you have to process from the top layer. Okay, so perhaps you can actually reduce the amount of packet that being sent into this frame. And with respect to that, your collision, perhaps when you detect, you can just send the very small frame. Okay. And then the third difference is that with CSMCD, you can send a jamming signal to identify all the user to stop transmitting because you have identified there's a collision, right? So that's the three difference between Aloha and CSMACD. So in CSMACD, there are these four type of actually three types of level. Okay, basically you have when idle, okay, no signal basically. Okay, so you have this one, no signal, no energy lah basically. When you have collision, meaning that you have high signal. Okay, and when you are idle, is a normal one. So idle, energy is zero level. Okay, so here it defines energy is zero. Busy, normal level. So busy is on normal level with respect to this energy part. Okay, so this is your normal. This is your zero level, idle level, and this would be your collision level, right? And then to further improve, you have what we call CSMACA, where it is much more focused to wireless local area network. Okay, so CSMACA differ from the previous procedure in that it should be no access conflict after data is sent. Okay, so how do you deliver this? Okay? So the procedure avoids collision by first checking the channel using one of the persistence strategy, okay, same as the CSMACD. And then after it finds the ideal line idle, the station wait for a period of time called the interframe space or IFS. Okay, so it will have this information of interframe space. Okay, so what this interframe space would do? This is the problem. Even though the channel may appear idle when it sends, the distance station may have already started transmitting. So IFS times allow the front of the transmission signal by the distance station to reach this station. So basically, it gives some more period of time by identifying what is the time of the longest distance to be traveled. Okay. So after waiting for the IFS time, if the line still idle, then wait another random amount of time before start sending. Okay, so you have a contention window. So basically, so this is the diagram. So when you try to send and everything is busy, okay, and then suddenly you found that there's an idle period. So this is the maximum time between you and the longest distance. Okay, so then you will actually try to do actually slot, okay, this within the contention window. So you can either slot in these windows, this windows, or the last window. Okay, so basically it by doing this, okay, you have already have some ample period of time to distance yourself from the longest distance. And then also here, if there's still any other packet or sender sending, so perhaps it can choose the random contention window. Okay, so what is this random contention window? Okay, so you have the IFS. So the IFS, okay, when the session is found, the session does not send immediately. It waits for a period called the interframe space. Okay, after waiting the interframe space, IFS time, if this channel is still idle, the station can send, but it still need to wait a equal time for the contention window. So a contention window here is an amount of time divided into slot. Okay, so you have to divide it into slot so that each station or each sender will actually select the different steps. So the station that is ready to send, choose a random number of slot. Okay, rather you send directly, you slot them into some period of time, and you have to wait for your time before you try to send. Okay, and the number of slot in the window changes according to the binary exponential back-off strategy. This means that it is set to one slot the first time and then double each time, and the station cannot detect an idle channel after the IFS time. Okay, so when you do this, okay, so we call it a slow start mechanism. So you start with 1 and then you go to 2, 4, 6, 2, 4, 16, okay, and then 32 and so forth. So you double it up. Just because you identified there's no collision or there's no error, so with respect to that, your transmission will be much faster. Okay, and then you also have this acknowledgement, positive acknowledgement. Okay, and this positive acknowledgement and the timer can help guarantee the receiver receive the frame. So you have still have the positive acknowledgement and this TTL, okay, timeout timer. When you start to send, you start the timer. So with respect to that, you can also see that CSMA can also be further improved with network allocation vector. Okay, by having this request to send, clear to send. Okay, so RTS is actually request to send, and CTS is clear to send. And then you have your acknowledgement, okay? And the NAB over here is considered as what they call it, network allocation vector, okay? Meaning that nobody can send, it's just for sender between A and B, okay? So you can further improve this lah, okay? So how does this happen is that before you send, you will need to request, okay, to be sent between A and B. And then B will actually reply saying that, okay, A is trying to send to me, okay, please clear the channel. Okay, so CTS will be sent not just to A, but to the rest of the channel. Okay, and then A will try to send, and when it finished, B will acknowledge, and you will also B will also send to the other user. So while on this time, okay, so nobody can send to B lah, okay, because the channel will be collided if you do that. So this is how you can improve. Okay, before sending the frame, the source station sends the medium by checking the energy level. Okay. And you use the interframe, okay, and so forth. Okay, so so this is the NAV. The station that are affected by this transmission create a timer called a network allocation vector and shows how much time must pass before this station are allowed to check the channel for idleness. Okay, so rather than you have to check every time with the NAV, the rest of the user can detect after some period of time that being identified by the NAV itself. Okay? Right. So that is on the random access. Then we also have what we call control access protocol. Okay. So with this control access protocol, basically what we can do is that we try to do reservation. Okay. Or perhaps we will ask anybody that wanted to send, okay, and then we give that channel to the one that having things to send, okay. Perhaps we just use the token passing where you can ask everyone if you have any other user that wanted to transfer. So basically for this part is the reservation method, okay. For random one is you don't reserve it. Okay, you just send whenever that you want to send. Okay, so this one, the channel itself is being reserved. So the time is divided into interval. Okay, and each interval, a reservation frame precedes the data frame sent in the interval. Okay, so here is where you have this control channel where you have 5 users being identified over here. Okay, and any of the user, if they wanted to send, they will need to show or give the indication that they want to send. Okay. So if you look at this part, okay, the first one on the right hand side over here, you have 5 users, okay, and only 1, 3, and 4 is trying to send. So with respect to that, you will reserve the next 3 frame over here for station 1, 3, and 4. Okay. Whereas the next control channel, it mentioned that only 1 will be standing. So you just reserve this for your station 1. Okay. Whereas the third one, okay, nobody is trying to send, so you just empty the next slot and waiting for the control mini slot. Okay. So this is for reservation. Okay. While for polling, okay, you need to have a primary station and secondary station. Okay. So when you have a primary station, this primary will play the main action or the primary station is actually the one that controlling the transmission. Okay, so it will ask, do you have anything to be sent? Okay, so if yes, you'll be given the chance to do that. Okay, or be selected. Or else, if you don't do that, you won't be able to send. Okay, so everything must gone through the primary device. Okay, but the problem is that when the primary device is has a problem, okay, or the station fails, then the system will totally down. Okay, so that is on the polling. So on the polling, where you have the primary, you will need to select, okay, or if there are different you have to either select or poll. In the select means that the primary will assign to channel here. Okay, see that channel B will acknowledge, and then you have send data and you acknowledge. Basically, this is ineffective because perhaps B doesn't have anything to transfer, so it's a waste of giving this channel. Okay. In a poll, okay, it will ask everyone if you have any data to be sent. So here it asks A. Okay, A says that with a negative acknowledgement, meaning that it doesn't need to send anything. Okay, so it stopped giving the channel to A. Then it sends another poll to B, and B says sends a data. Okay, and then primary will acknowledge. Okay, so these are the difference between select and poll. Then we also have what we call a token passing, okay, such as a ring network. Okay, so in a token passing, basically as mentioned, every user, if you have any data to transfer, you have to wait for the token to arrive at your station. Okay, so wait for the token. Then if you wanted to send, you capture the token and you append your information or data to the token and then send the frame. Okay. Then if the time expired, okay, meaning that here when you have a frame, then you can send multiple frame at one time until your time of being given is expired. If no, you can send another frame. If yes, you have to release the token, okay, and it will be given to the other user lah, okay. And if come back to you, then you can come again, send the information. So token management is needed for this access method. Okay, station must be limited as the time they can have possession of the token. So this will be limited by the time. Okay, but for fiber optic, as we mentioned, basically the time is in microsecond and nanosecond of transmission. So although it depends on time, but basically for fiber optics, it can really have very small period of delay lah. So the token must be monitored, okay, as it's not being destroyed or lost, okay. And other than that, priority lah. The token management need to make low priority station release the token when you have high priority station. Okay, so perhaps this will need to be implemented if you have low priorities and high priorities. Okay, so but in current situation, the packet itself has some information on how the identification of the priority. Okay, so the priority on each of the packet will depends on application. Okay, if you have a kind of a online kind of transfer. Okay, so real time when you have like for call or you have to play real-time video or whatsoever, so you'll be given highest priority compared to other like packet sending or receiving a small data packet. Okay? So this is where you can have the token passing being deployed in what we call a physical link. Then you can also have what we call a dual ring, okay, both on both direction, okay, or you can also put it into a bus ring, okay, or a star ring, okay. So this is how the token passing will happen. And last but not least, we have what we call channelization protocol. So basically here, your whole frequency band will be divided into time, frequency, or code, okay, or even orthogonal description. With FDMA, basically you are manipulating your frequency band. Okay, so if you have 10 megahertz of band, so perhaps you give 1 megahertz for one user, so you have 10 users that can be used at one time. Okay, so this is what we call frequency division multiplexing. Okay, so here in this diagram, you can see that each user is being given the full frequency band. Okay. But with some limited time, okay, that you can have more user, okay, but you can see that this user, the signal is being what we call modulation, okay, is you have a carrier frequency that modulate to your signal, okay, so this is the frequency for channel number 1, then the second one, okay, the third one, and the fourth one. And on the channel, you can see that when they share the channel, each and every station have its own frequency range lah, that you can submit. Okay, so the frequency over here, okay, is the bandwidth of the whole signal, and the blue one here is actually the bandwidth. Because this is one bandwidth. Okay, this is the bandwidth of the green, orange one, the white one, and the yellow one. Okay, so this is the with FDM. Okay, then you can also manipulate it based on time division. Okay, so the time division where you actually allocate different time for your different station. So basically you have the whole frequency band. Okay, bandwidth here is the total bandwidth. Okay, so this is the whole bandwidth, right? And then you have this different time being given so that you're able to give some period to each and every user. Okay, so just now is based on frequency, now it is based on time, right? So you have the whole bandwidth, but we have limited of time. Okay, so this is how it's being shared with TDMA. And also we have what we call code division multiple access. Okay. Okay, so this one is much more tedious and very specific. Okay. So so simply means communication with different code, meaning that instead of you use the frequency band and also the time band, okay, so now you use code, okay, where you have to identify each transmitter with a code. So one of the beauty of using this code is that only those who have that intention or have the the access, okay, to that specific sender and user, those who only have that code will able to uh, get the information, okay, or else you won't able to get it. Okay, so CDMA differ from FDMA in that only one channel occupied the entire bandwidth of the link. Okay, so you have only one channel rather than being classified as frequency. Now it's only one channel with the different code. And it differs from TDMA in that all stations can be sent data simultaneously. There is no time sharing. Okay, it's not being shared. Okay, so it's based on the code. Okay, so the idea here is that you have 4 stations, and with respect to the 4 stations, you will have different code for different stations. So here you can see that if you have this 4 number of stations, and you will need to multiply your station A with your code. Okay, so the data by is code to get D1. Okay, C1. So basically, this is your code. Then you have to multiply with D1, and station 2 need to be multiplied by code of D2. Okay, to get your C2, and so forth. Okay, and when you transmit on the chat medium over here, okay, so you can see that it's a combination of your information of D1 with the code of C1, okay, your information of D2 with your code of C2, your information of D3 with a code of C3, and your information of D4 with a code of C4. Okay, so you combine all together to be sent directly on the same channel. Okay. So station 2, okay, basically example here, station 2 wants to hear what station 1 is saying. So here, this one, they want to know what station 1 is trying to send. Okay, so it will multiply the data on the channel by C1. Okay, C1 is the code for channel 1, and the code C1, the code of channel 1. Because C1 times by C1 is 4, but C2 times C1, C3, the rest, okay, it will all get 0. Okay, station 2 divides the result by 1 and get the data from station 1. Just a minute. I have something urgent. This card, give me 1 minute for me to address my problem. Sorry for the delay. So basically right now, if you wanted to get the channel or the information being sent by that specific channel, you need to have the code for that specific channel. Okay, so So you need to have the data. If you want to get the data from D1, okay, D2, your section 2 wanted to get this information D1, so it needs to be multiplied with the C1, okay. So here it says that because C1 times by C1 is 4, we'll see later. The rest C2 times C1, C3 plus C1, the code multiply with the other one, it will give you 0. Okay, station 2 divides the result by 4 to get the data from station 1. Okay, so now you can get the information from D1. Right? So these are the code that perhaps you can use. Okay, for C1, this is plus 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 plus. Okay, C2 plus 1 minus 1 plus 1 minus 1. And this being the chip sequence that being generated by the chip. And basically, if you multiply it together, you will get the different values as being shown in page 57 over here. Okay, so if basically says that if you have the information from not the one that have or wanted to receive the information correctly, so you when you sum this everything up, you will have zeros. Okay, whereas if it's okay, then you will have 4 lah. Okay, so now you have 4. Okay, for this one, have 0 for this one. So only those who being assigned or intended for the information will get the information basically. So for CDMA, okay, the data you don't have a 0 and 1, okay, but you have 3 level. You have the silent where the signal voltage is 0. You have bit 0 when the signal is minus 1. You have bit 1 when the signal is plus 1. Okay, so this is where you can see that when you combine it together, okay, so you'll be able to identify with respect to the information of the code. Okay, so you can actually get this using this what we call wash table. Okay, so that you're able to get the information directly. Right, so for example here, find the chip for a network with 2 station and 4 station. So for a 2 station, perhaps you use plus plus and plus minus 1. Okay, and for 4 station, you have to have different combination, although you can have more than this. Okay, so what is the number of sequence if we have 90 station in our network? Okay, so to the power of m, okay, number of sequence where m is equals to 7, okay, which is the maximum that we can have more than 90. Okay, if you go to the power of 6, you have 64. Lesser than that, so you need to go to the power of 7. So we can use this for the 90 sequence of the chip. Okay. And then prove that the receiving station can get data sent by a specific sender if it's multiply the entire data or the channel by the sender chip code and then divides it by the number of station. Okay, refer to figure 27. So basically, if you get the code correctly, okay, so you will get the specific information. Okay, so here that is proof that this is the first station using our previous 4 station example. We can say that the data or the channel D is D1, C1, D2, C2, D3, C3, and D4, C4. So this is the one on the shared medium. The receiver which wants to get the data sent by station 1 must multiply this data by C1. Okay, so so the information D divide times by C1 divide by 4. So you can express it in this expression, okay, and eventually you will get that your D1 is being defined over here. Okay, So with that, I think this is the last slide for today. Before we want to go to our quiz too. Okay, so what we have seen right now is that for a channel that needs to be assigned to multiple user, we need to have what we call media access control. It's a protocol that have several variation. Okay, so we have the one that random, we have the control one, we have the channelization one. Okay, and with the random one, we already seen that we can use the simple one as Aloha, and then you have the CSMA, CSMA with CD, CSMA with CA. Okay, and then for the control, okay, so you have uh, for reservation, polling, and also token passing. Okay, and for channelization, you can say that you have the FDMA, TDMA, and CDMA. Okay, so these are the media access control. Okay, sublayer of the data link layer in your OSI model. Okay, with that, I think that is my sharing of my for today. Do you have any question? Uh, a bit dark. Okay. Basically, I think if I would just want to show you guys, I actually on the 26th floor now in one of the hotels that being used for this conference. Basically, I'm one of the organizing committee for this conference. We call it GlobeCom. Okay, and it's a flagship conference for Communication Society. And this is the first time that we bring this conference to Malaysia. And we have successfully have 2,200 participants for this conference. Compared to our expectation is around 1,500. Okay, so we have a lot of participants from outside. Okay, from mainly from China mainland, also from from American continent and so forth. Okay, so I'm open if you guys have any question. Right. Actually, our conference is in KL Combat, but I cannot show you the area of KL Combat now. Just can show you that is my views. Things might get a little bit physical. Okay, yeah, you get much physical after this. Oh, this location, this is Grand Hyatt. Uh, Basically, they are a bit confused in this hotel where you have your lobby is on the 39th floor. So you have to actually check in on the 39th floor, and then you can access to your hotels going down rather than your lobby is on the ground floor and move up. Okay, so if there's no question, I wanted to flash now for the quiz. Okay, so now it's 11:41. Um, attendance is already been given, but I can also share it you. Okay, thank you very much, Haris, for sharing back the attendance list. Okay, or perhaps if you want to scan, this is the attendance list. All right, post the link in the Google Classroom. Oh, okay, sorry.
Sir, I meant the link to the quiz. Sir,
All right. So, what I try to say, when is the quiz link? Oh, where is the quiz link? Not yet, not yet. You guys ready? Huh? You guys ready? If ready, then perhaps I can get the quiz link now. Wait. Uh, you already shared. It's okay. So create materials quiz two. Right. So you have 10 minutes from now. It's 11:46. I will stop. The form is 11:56. Okay. So please go on and answer uh, quiz right now. Where is it? Okay. So this is the quiz. You have 10 minutes to answer every question. Please help yourself and start with the quiz. Another 2 more minutes to go. One more minute. Okay, 30 seconds more. Okay, we have currently 116 altogether. Everyone has submit. I give another 10 seconds. And 125, right? Responded. Okay, so anybody else want to submit? If not, I will stop for the response. Okay. All right. Thank you very much. I think by now you can see the solution or the result in your email. If not, I'll look into it later on. Okay. So before we go, any question or anything that you want to highlight? Is the test will be conducted next week? Yes, the test will be conducted next week. The time will be mentioned later on because everyone will be having the same test on the same time. Next Monday we should be on holiday. There's a public holiday next Monday. What do you reckon? I can have it online, but physically I don't think the lab will be open. So you can feedback me through the Google class, and we'll set the replacement for that class for those Monday sessions. What, online or physical? What you mean the for the test? Is it? It's online, but it's will be what do you call it? Structure lah, rather than MCQ. No MCQ at all. No. Everything will be based on structure. Anything else? So I think that will be it for today. So hope that I can see you guys physically next week. And if you have any problem, then with the test result out, let me check back. But actually, the setting I do it so that the marks will be released directly. So never mind, I'll check. If it's not, then I will share through Google Classroom later on. Right? Okay, so if there's no further question, thank you everyone. Okay, and I'll see you again for the next session. Okay, bye.